Okay, so let's go ahead and get started. Today is going to be a review for the exam. I should post the exam to Blackboard um, probably tomorrow evening. Um, this exam will be timed, and you can take it whenever you want in between the time I post it and next Wednesday. So, or next Thursday, depending on which class you're in. Um, But yeah, so there'll be detailed instructions for you, and it shouldn't be too hard. My first exam is typically pretty easy, so I will be posting it soon. Okay. The exam, I think I'm going to decide on uh, 4 hours continuous time to take the exam. And you write your, actually, I'll show you. Give me a second. Um, So let me share my screen. Okay, so this is what the exam will look like. This is an exam I gave to my students in the spring. So notice here that there's a pledge right here um, that I want all of you to follow. So you're allowed to use your notes and you're allowed to use the textbook, but you're not allowed to talk to anyone else. Um, and you're permitted 4 continuous hours to work on the exam. You have your start time and your end time here, where, and then you print your name and then sign your name saying that you acknowledge that you followed the rules, being that you didn't talk to anyone else. I'm trusting all of you to follow these rules. And yeah, so it's actually, I'll go ahead and like show you some of the problems that I gave for this previous exam. It'll be very similar to what you get. So we have a compound proposition, and I ask that you prove that it's a tautology. You can do this using logical equivalences, and we'll do some example problems like that today. Translate mathematical or logical statements like this into English sentences. Okay, so for example, here for all x, for all y, x less than 0, y less than 0 implies x times y is greater than 0. So the English translation would be something like the product of two negative numbers is going to be positive. Um, and then we have a proof here. We've done a few of these in class. We'll do some more today. Another proof involving rational numbers. So definitely there'll be one proof where you have like even or odd type of things, and then one proof where you'll be asked to prove something about rational numbers. Ignore this, we didn't get to sets. We're going to start set theory next week. But this is what it looks like. It's pretty simple, straightforward exam. I'm not going to give you these exact same problems, but I will give you something very similar to these. Okay, so, all right, so let's do some practice problems here. So, let's start with the following claim. So, claim P implies R, and Q implies R is logically equivalent to P or Q implies R. Okay, so we can prove this using a list of logical equivalencies. Proof. So I would typically like to start on the more complicated side. So the left-hand side of this equivalence looks more complicated. So let's go ahead and start there. Okay. So this is logically equivalent to, well, I personally would like to get rid of the conditionals first. So this is logically equivalent to not P or R, or, oh, sorry, and not Q or R. Okay, so and this was by star. That's the rule that, so star, if you recall, is that if P, then Q is logically equivalent to not P or Q. So I call that rule star.
Professor,
Yes.
in the book, that same star rule is called the conditional identity rule. Can we use either or on the exam, or would you like us to use the star rule?
Either or, that'll work.
Thank you.
Yeah, I didn't know that though. I didn't know that had a name. I've always called it star. But thank you for letting me know. Okay, so we need to somehow get to this side here. Let's see, how can we do this? I see that I have an or, and and. So it looks like I can take out, and let's say, so I'm gonna just write it another way so you can see it a little bit better. Or Q, and this is by associativity. I have a room with associativity. Okay, and then I see this looks like a distributive rule here. So if you had been using the Rosen textbook that I posted a link to, let's see. So there should be a table that looks like that somewhere in your textbook, and if it's not in your textbook, then it will be on the Rosen book. And we can look here and we see something that looks like maybe a distributive law has been applied here. In particular, this looks like R or not P and not Q. Okay? So this is by the distributive law. Okay? So need to somehow get to that. Well, I can rewrite this as saying by associativity. Okay, so that's by associativity. And then maybe I can apply De Morgan's law here. So take the negation out. So this is by De Morgan. Okay. And then we're there, right? You see it now. Because here, by that star rule, this is equivalent to if P or Q, then R. That's by star. And then we're done. So we've established that this, the left-hand side is logically equivalent to the right-hand side just because you can follow down the string of logical equivalencies and get to the right-hand side from the left. Now this one might seem a little bit tricky for you because, well, in the past, I've noticed that students, when they encounter something like De Morgan's law, so if they have like the negation of P or Q, that's logically equivalent to not P and not Q, right? That's De Morgan's law. Well, for whatever reason, students tend to look left to right on this. They think that they can start here and then go there. But they never remember that this is a logical equivalence. You can also start here and go there. right? So here, you see that I went in the reverse direction. I went from there to there. So just always remember when you're looking at these logical equivalencies that just because we read left to right doesn't mean that we can't go from right to left. That's just, again, something that I've noticed with my discrete math students over the last 5 years. Okay, so always be careful about that. So remember, you can go both ways. For example, even right here, going from this to the implication, it's, again, so P or Q implies R, it's logically equivalent to the negation of the hypothesis, or R. So just because I go left to right, I can also go right to left, and that's what I did here, from there to there. Okay, so again, just please pay attention to that. Okay. All right. Next, let's look at negating a statement. Okay, so find the negation of, say, for all x less than -1, or x greater than 2. Okay, so I'm definitely going to give you a problem like this, where I give you some compound proposition with a predicate in front, and I'm going to ask you to find the negation of it. So let's do this. Solution. So let's go ahead and negate this. So if you recall, when you negate the universal quantifier, you get the existential quantifier. So this is going to be logically equivalent to there exists x, and then you negate the compound proposition. Okay, but we're not done. We need to also negate this statement in here. So we see that we have the negation of an or. So by De Morgan's law, this is going to become negation and negation of that. So this will be there exists x, not the case that x is less than -1, and not the case that x is greater than 2. Okay? Almost done. So if we negate x being less than -1, we're going to get that x is greater than or equal to -1. And then if we negate x greater than 2, we get that x is less than or equal to. And then we're done. So when I'm asking you to find the negation of something or to find a value, I'd like you to, on the exam, you use like a blue or red pen or some different color than what you're writing in, and just kind of box in your last step so I can clearly see what you mean to have the answer. Okay? All right, so let's do another problem. Okay, so to prove the product of two odd integers is odd. Okay, so over here, I'm going to write my formal proof, and then over here, I'm going to write my scratch proof. Okay, so we can prove this statement with a direct proof. So okay. So we need to introduce some variables to represent these odd integers. So we'll say something like n is odd and m is odd. Okay. So once we've made that assumption, we can then recall the definition of being odd. So that means that n is equal to 2k plus 1 and m is equal to 2j plus 1, where k and j are integers. Okay. So now that we've referenced the definition, we need to look at the product of these two things. So again, n and m are just arbitrary odd numbers. Okay? So then n times m is equal to 2k plus 1 times 2j plus 1. Okay. So then we have a little bit of algebra to do. This will become 4kj plus 2k plus 2j plus 1. Okay. Now we need to make this look like an odd integer. So I see that the first three terms here have a factor of 2, which I'm going to factor out. So let's be 2 times 2kj plus k plus j plus 1. All right. So then we're done, because now we have that this right here. Let's see. So this is an integer, so we're done. Okay. But this is not what you're going to write for me. This is your own stuff, right? What you're going to write is the formal proof using the scratch work to guide you. So we'll go ahead and start this off by declaring n and m to be odd. So let n and m be odd integers. Can someone guess what the next line is going to say? Anybody?
By definition.
Right. So then by definition, there exists integers k and j, so that n is equal to 2k plus 1 and m is equal to 2j plus 1. Okay, so therefore, maybe use n times m is equal to 2k plus 1 times 2j plus 1, which is equal to 4kj plus 2k plus 2j plus 1, which is equal to 2 times 2kj plus k plus j plus 1. Okay. And then we finish it off by saying since 2kj plus k plus j is an integer, n times m is even by definition.
Don't you want to say odd?
Oh, odd. Thank you. Okay, so that establishes the claim. It's true. We've shown it to be true, and this is what the formal proof looks like. Now, it's very straightforward to get full credit on this type of problem. Write it as closely as you can to how I would write it. Make your declarative statement, recall the definition, do some algebra, restate the definition, done. Exactly like this, and you'll be fine. Okay. And if for whatever reason you get stuck on a proof and you're not able to finish it, you can also include your scratch work, so I can look at your scratch work and try to give you some type of points, even if you weren't able to write the full proof down. Good. Okay, so that's a proof involving odd numbers. Next, let's look at a proof involving rationals and irrational numbers. Okay, so prove the sum of an irrational number and a rational number is irrational. Okay, so as before, we have our formal proof here, and then our scratch work here. Okay, so anytime you see a statement involving irrational numbers, more than likely you're going to use a proof by contradiction. Okay, so I think that's how we should proceed with this problem. So contradiction. Okay, so the way we can do this is by saying maybe x is irrational, y is rational. By way of contradiction, we're assuming the sum is also rational. And x plus y is rational. Okay, so we've made our assumptions. So we next recall the definition of being rational. What that means is that y is equal to a over b, and x plus y is equal to c over d, where A, B, C, and D are integers, and B not equal to 0, and D not equal to 0. Okay. So now we need to search for the contradiction, the
Excuse
false.
me, sorry, real quick. What is it based on again? It's P or not P or Q when you do a contradiction?
For
What is it?
So for contradiction, um, let's say, you assume P and not Q and show
P
that
and not Q. Okay, thank you.
false. So
Okay, thank you.
the P here is, so that's your hypothesis. If X is irrational and Y is rational, then, so this right here is your not Q.
Okay,
Okay. So
perfect.
if you look at this statement here, what it's really saying is that if X is irrational and Y is rational, then X plus Y is irrational. That's what the original statement is. So here we're assuming that it is rational, which is the negation of that original conclusion. So now that we've used the definition here, we need to get to the contradiction, the false implication that's going to occur. And typically with irrational proofs, you're going to get that something is irrational and then show that it's also rational, which both those things can't happen, and there's your contradiction. So the way that we can do this here is we can say, so X plus Y is equal to C over D, but we can replace Y by A over B, which means that X is equal to C over D minus A over B, but that's equal to CB minus AD all over DB. All right, so, and then here we're done because that's an integer, and D times B is not equal to 0 because both D and B are not 0, so the product is going to be not 0. So this is a ratio of integers with non-zero denominator, which leads to a contradiction. Whenever I do that little symbol there in my scratch work, I mean contradiction. So X is a rational number by definition, but in our original assumption, X is irrational. It can't be both, that's the contradiction. So now we should piece this together into a formal proof. So whenever you're doing a non-direct proof, when you're doing an indirect method like contrapositive or contradiction, you need to state to the reader on the first line that you're doing so that the reader understands the type of proof that you're proceeding with. So we can say something like, by way of contradiction, assume X is irrational Y is rational, and X plus Y is rational. Okay, so then I checked off that mark there, so now we're at the definition part. So we say, then by definition, there exists integers A, B, C, and D with B non-zero and D non-zero, so that y is equal to a over b, and x plus y is equal to c over d. Okay. So then, therefore, x plus y is equal to c over d. But this is the same thing as saying x plus a over b is equal to c over d. And this is like saying x is equal to c over d minus a over b. And I would write one more line, but I'm running out of room, so I'm just going to write it right here. cb minus ad over d times b. Okay? And then you just have to finish it off by saying since cb minus ad, comma, db, since those are integers, with d times b not equal to 0, x is rational. A contradiction. And if I had more room, I'd probably write it. A contradiction since x is also irrational, or something like that. With proofs, you want to be as descriptive as possible to the reader so that they can follow each line and reference back information. So I know I finished it here, but again, it would be more clear to the reader if you said a contradiction since x is also irrational, which the reader can then go up and look, oh, we assumed that x was irrational. Okay? So, I think that's all I've prepared for the review because that's roughly going to be the types of questions that you're going to see. So what I can do for you now, let me share my screen. Okay. So I'm going to go ahead and open up the previous homeworks until this Sunday. So if you've missed any of these, you can go back and get more practice in for the exam. And then also just review the problems that we did today. Okay. All right, so yeah, that will be it for today. So if you're missing any of these problems, please, because I'm opening it back up for you, go back and get those homework assignments in.
When will the exam be?
I'm going to probably post it to Blackboard tomorrow.
Okay.
And once I post it, you have until next Wednesday to turn it in. Well, not until, you will turn it in to me next Wednesday, but you can take it any day that you want in between now or when I post it in next Wednesday.
Okay. And we take it to you directly?
You'll scan it or take pictures of it and email it to me.
Okay. And then email it? Okay. Okay.
Yeah.
Thank you.
But yeah, so homework's open for everyone. Don't stress too much about it. it's going to be just like the problems I did today. And I even showed you my previous exam so you have an idea of what it looks like. So good luck. I hope everyone does well. And hopefully everyone is staying safe out there.
Quick question. As far as the homework, it was only the first chapter and the second chapter that we submitted so far, correct?
Correct.
Okay.
And somebody asked how we turn the exam in again. He said just email it after you scan it in, is what he said.
Right.
Somebody else asked through the chat.
Yeah, so you're just gonna scan it or take photos of it with your phone and send me those photos.
Cool. Thank
Okay.
you.
And if you don't have a printer and you're not able to print out the exam, you can write out all the problems on your own paper. Just please write them neatly and include your start time and end time.
Cool. Thank you.
All right. We'll see y'all next week.
Thank you.
Thank you.
Thank you, Professor.